Welcome to the 2-1 podcast, and this is start chapter 2, which is about mechanical equilibrium. And basically we're going to be talking about mechanical equilibrium being stable, that when things stable, meaning that there are no change in motion. That doesn't mean it isn't in motion, it's in motion, but there's no changes in motion. So like I just said, things are stable without changes in motion. And in this case, these rocks are in mechanical equilibrium. In this case, in order for them to change their state, an imbalanced force would have to change their resting state. You would have to have an external force that would do some kind of change to their state there. So what do you need to change an object's state? We're going to need a force to change it, and that's the idea behind 2-1. We're going to define what a force is. A force is, this is a classic definition, a push or a pull. And you always have to have a force to change the state of motion. That doesn't mean you have to have a force to have something have motion. And we say when we combine all the forces together, we get what we call the net force. That's looking at this girl's pushing combined with this guy's pulling. What's the net force on that box? And our unit for this is the Newton, which is abbreviated with a capital N. The unit of force is a Newton, and it's named after Sir Isaac Newton, of course. So let's look at these here. If you look, what we're saying here is that the net force depends on the magnitude and in what direction they are. Here we have two forces. Let's change the pointer to a highlighter. Here we have two forces. One's 5 newtons, one's 10, and they're both going in the same direction. So our net force is going to be 15 in that direction. The next one here, now instead of the two forces being in the same direction, one's in one direction, the other's in another direction, and they're going to subtract from each other. So we're going to end up with only 5 newtons. It's a smaller force. And the last one, if you notice now, this one's only 5 newtons. This one's 5 newtons. They're equal. They're in opposite directions. So we're going to end up with no force on the object at all. Here we see a girl. There's another situation where there's no force on the object. The girl here is pushing the apple upward. This is the girl's force here. And then the earth is pulling it with gravity down. And they are equal and opposite. So we end up with there is a 0 in net force. So the net force on the object is 0. It doesn't go anywhere. Spring. We need to define the word tension. When you stretch a string, you're putting it under tension. And tension is it's a stretching force. So its unit is going to be in newtons. And not only is the stretching force going to be in newtons, it's also going to be in weight. And when the English units, we use pounds, whereas we use pounds, whereas in the SI unit we're going to use newtons. So here's a little table to show you. The old unit, the one you're used to, is a pound. We describe to each other how much we weigh in pounds, but the new unit is in newtons. And the conversion is 1 newton equals 22 pounds. Now here's a scale here. This scale, there's nothing on the scale. So the scale is set in such a way that nothing is read on it. There's no tension on the spring. There's nothing hanging from it, so there's no tension. Now we put a bag of sugar on it, and once the sugar's pulling on a spring inside, and the bag of sugar here weighs 2 pounds, which also translates to 9 newtons. The bag is not moving, so the net force on the bag is 0. So there are two forces acting on the bag. The first force is the tension force pulling it back up by the scale. The second force is going to be the weight pulling it down. They are equal and opposite, so therefore the net force on it is going to be 0, so it's at rest. It's balanced. Here's some force vectors. We did a little work on this before, so we kind of know what a vector is. Vector has magnitude and direction. In this case, this one is a magnitude of 316 and an angle of 35 degrees north of east. When you have a vector, once again, you have to have magnitude and direction. And we're going to see that force is an example of vector quantity. It has magnitude and a direction. The opposite of a vector quantity is a scalar quantity, and it only has magnitude. And so some properties of that are time, which doesn't have a direction; area doesn't have a direction; it has a location but not a direction; and volume, which doesn't have a direction. The concept on this slide is that the vectors are proportional depending on how long they are. And in this case, for every 1 centimeter, the force is 20 kilometers, the vector is 20 kilometers per hour. So in the end, that should be 20 newtons per centimeter. So in that case, then the force is equal to 60 newtons to the right. We gotta change that. So this is just a reminder that you can add and subtract vectors, but in the end, two that are added together would be equal to 5, but two subtracted from each other would only be a vector of 1. So in the end, the direction matters of the vector. It's very important. So how can we change an object's state of motion? What you're going to do is by applying a force to it.